And Peyton, if at any point you get like distracted by our talking, you can feel free to go to the lab or something.
Okay.
All right, 8.1, integral as net change. So we're going to kind of be going back to linear motion.
Wait, how did we do linear motion?
Like position, velocity, acceleration.
Is that chapter 5?
6.
That was chapter 6.
Chapter 5 was the
Chapter 5 was the
awful
the
chapter.
evil chapter.
The everybody wants to cry chapter. So we had position, velocity, and acceleration. And position we would say was S of t, right? So how did, when we were given position, we get to velocity?
Derivative.
The derivative. So v of t is equal to s prime of t. And how did we get to acceleration?
Second derivative.
Second derivative. So a of t is equal to b of t, or the derivative of v of t, or is equal to the second derivative of position. So s double prime of t. So now we're kind of going to be working opposite, right? Because we did all this stuff when we were doing derivatives, but we've been using integrals, so you should expect that we're going to be using integrals now to do all of this stuff. So some of it's going to be like finding a position at certain times when you're given acceleration or velocity or something like that, or finding distance traveled is kind of a big thing. You're also going to notice that a lot of these are word problem type questions. And so the strategy for modeling with integrals. First, we're going to approximate what you want to find as a Riemann sum of values of a continuous function multiplied by interval lengths if f of x is the function and the interval a to b, the interval, and you partition the interval into subintervals. Of length delta x. The approximating sums will have the form summation of f of c sub k delta x with c sub k a point in the kth subinterval then 2, write a definite integral here the integral from b to a of f of x dx to express, I feel like that's backwards, so that's what the book says. The limit of these sums as the norms of the partitions go to 0. And then 3, evaluate the integral numerically or with an antiderivative. So the stuff I've highlighted is kind of like the key stuff for that. So this could help us with like the consumption over time, like how many like peanuts were eaten in a year, or something like that. Like kind of random, but so now's where it gets into the physics stuff a little bit. So we've got work. And so we know that work done by the force is W equals FD, which is also known as the constant force formula. So force times distance. So in physics, does anybody remember what we said the units were for this? A joule. So a joule or a Newton meter would have been what it is in metric. But in the American system, this is now something new for you to learn, the unit of work is called a foot-pound.
I don't like it. Too bad. Yeah, I don't understand why our country's just like weird when it comes to like.
Who knows? I would rather deal with metric. It's so much
Yeah,
easier.
because it's all
Because everything
hours
is,
and-
yeah, it's all consistent. It's just easy. Like, once I do, like, physics, so, like, obviously last year I didn't do physics, but, like, once I, like, teach physics for a while, I feel like it's really hard for me to, like, go back to, like, American units, like, with stuff like this. Because, like, several of the problems in the book are, like, something in foot-pounds. I'm like, can we just use metric? Like, please. But it's fine. Hooke's law. Is the force that it takes to stretch or compress a spring X units from its natural. So basically, just like where if you just like laid the spring on the ground and nothing was touching it, pulling on it, squishing it, like where it would sit would be the natural. Is a constant times K, so F equals KX. And K is the spring constant for that. K is measured in force units per unit length. And that's called the force constant. So now maybe you're, like, we haven't done the problems yet, but maybe now you're starting to see why I said I had to take university physics, which is physics using calculus, because things that we did in physics with algebra, you can also do with calculus. But I don't understand why we had to do it with calculus when it works with algebra. That's much easier. But nonetheless, it's things. So we have to learn it. All right, that's all the notes I'm going to give you.